Hi everyone, so today we're going to talk about some other roots. We have been exploring square roots up until now, but there are other roots, as you know. There are cubic roots, there are fourth roots, okay, and we're going to explore all of the radical forms as well as exponential forms of these different roots. So we see that radical expressions can be written in more than one way. So in radical form, we know that the square root of 25 looks like this, okay? Now what you might not realize is that there is an invisible 2 that lives here, and there's an invisible 1 that lives here. So we're essentially taking the square root of 25 to the first power. Now if we look over here at the example written in exponential form, we see that the square root of 25 can be written as 25 to the 1/2. Okay, so notice where my 1 came from, right? That's in my numerator of my exponent, and where my 2 came from, the denominator of the exponent. So let's look at the next two examples, use that same thought process to write them in exponential form as well. So the cubic root of 27, again, you can think about that invisible 1, okay, that lives underneath, it's the exponent, 27 to the first power. So we can rewrite it as 27 to the 1/3. The fourth root of 16 can be rewritten as 16 to the 1/4. So the small number above the radical is called the index. Okay, so the index is the 2, the 3, and the 4 in these examples. When the index is not written, we know that we're implying that we're taking the square root. Now let's look to see what it means to be in simplified radical form. So the radicand, which is the number that lives underneath the radical, so the radicand of an nth root is as small as possible when it's simplified. And you all know how to do that so far, right? If you were given the square root of 8 and said make sure that it's written in simplified form, we would write 2 rad 2 because we want the radicand to be as small as possible, that 2 under there. Now, the root index is also as small as possible when simplified. And we'll see some examples of that in a minute. And thirdly, there, again, are no radicals in the denominator. Remember, we're always rationalizing the denominator. So the same rules apply to simplifying radicals as they do to simplifying with fractional exponents. So we're just rewriting a number in two different ways, one with exponents, one with radicals. And we can interchange them to help us simplify. So in the first couple examples, let's simplify from exponential form into radical form. So 25 to the 1/3, that's rewritten as the cubic root of 125 to the first power. Remember that invisible 1. Okay, so the denominator, remember, is the index. The numerator of your exponent is the exponent under the radical, or the exponent of the radicand. So if we rewrite it this way, now let's think in cubes. The cubic root of 125 is just 5, right? 5 times 5 times 5. Let's look at example B. We have 5 to the 1/2 times 5 to the 1/2. Well, 5 to the 1/2 can be rewritten as the square root of 5. So we have the square root of 5 times the square root of 5, which just equals 5. Now in letter C, I have 10 to the 1/3 times 100 to the 1/3. Think about how we can write that using radicals. So we're taking the cubic root of 10 times the cubic root of 100. remember your rules. You can multiply numbers that live underneath radicals together as long as the index for those radicals are the same. Okay, just like we could multiply square roots by square roots, I can multiply a cubic root by another cubic root because the index is the same on both of those. It's a 3. So when I do that, I get cubic root of 1,000. If I'm thinking in cubes, that equals a 10. Now, it's important to think in terms of your index. So for instance, in the first example we did here, letter A, we thought in terms of cubes, okay? Now, I want you to apply that when we're looking at these next few examples. We know the cubic root of 27 is 3. That one was nice and simple. Now, the cubic root of 8, what number times itself again equals 8? That's a 2. Okay, so we come to number 3, the cubic root of 16. Now, we'll notice that the first two, cubic root of 27, the cubic root of 8, those were both perfect cubes. 16 is not a perfect cube. It doesn't mean that we can't simplify it, though. I want you to think in terms of cubes. And try to break it down into a perfect cube and a not perfect cube. So the largest perfect cube that goes into 16 is an 8. So I can break this up into cubic root of 8 times the cubic root of 2, right? If we multiply those together, we get the cubic root of 16. So we can simplify the cubic root of 8 to just 2, and the cubic root of 2 is simplified as much as it can be. So our answer is 2 times the cubic root of 2. Number 4. Now, this may look a little strange because up until now, we've been dealing with square roots, and if we see a negative underneath the radical, we've only said that we can't take that, right? This year we learned that it could be an imaginary number. Okay, however, this is actually a real number. Okay, so think to yourself, does something times itself again equal negative 8? Well, if I have negative 2 times negative 2 times negative 2, that does equal negative 8, right? Negative 2 to the third power. So the cubic root of negative 8 equals negative 2. Number 5, let's use the same method as before. It's not a perfect cube, so let's try and break it up into a perfect and a not. Let's just write out a list to help ourselves of the first, let's write out the first 10 perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed 125, 6 cubed 216, 7 cubed 343, 8 cubed 512, 9 cubed 729, 10 cubed 1,000. So keep this list in mind as we move through this, and it'll help you to be able to pick out the largest perfect cube when you have to simplify, like in number 5. So the largest perfect cube that goes into 128 from my list is a 64. So I'll break it up into the perfect and the not. So the cubic root of 64 times the cubic root of 2. Cubic root of 64 is 4. And cubic root of 2 hangs out at the end because can't simplify that anymore. Now let's break down this cubic root of negative 54. Now, if you can, we want to move that negative outside of the radical. So we're going to take that with our perfect cube part, okay? So I can break this up into the perfect cube of a negative 27 times the cubic root of 2. Now, what does the cubic root of negative 27 come out to? Well, that's a negative 3 times cubic root of 2. Okay, so notice what I did. Because it's a cubic function, I took my negative, right, that lived under here, brought it with my perfect cube. That way it now lives outside of the radical in my answer so that it's simplified. So that brings me to this question here. You can take an odd root out of a negative, but not an even root. So why is that? And I know that we've discussed this earlier in the year, right? If you take a negative number multiplied by itself an even number of times, what happens to that number? Well, it becomes positive, right? If you have a negative, multiply it by itself any even number of times, it becomes a positive number. However, if you have a negative number, that you multiply by itself an odd number of times, think about what happens. Well, that number still stays negative, right? If I have -3 times -3 times -3, well, that equals a -27, right? Negative times a negative is a positive, but now positive times a negative makes our answer a negative. So keep that in mind when we're dealing with these, okay? We can't take an even root of a negative, okay? If we're trying to take an odd root of a negative, it is possible. So let's look at the next page. Number 7, the fourth root of 16. What number multiplied by itself 4 times gives me 16? Well, that's going to be a 2. Fourth root of 81, is there a number multiplied by itself 4 times that gives us 81? That's a 3. 3 times 3 times 3 times 3. Okay, number 9, the fourth root of -81. So you're looking at your index, you're saying it's an even root. If I'm thinking about simplifying this, I can't simplify this to something real because this would be imaginary. So I'm just going to write not real. Next example, does anything multiplied by itself 4 times give me 25? Does not. So I'm going to have to try and see if I can still simplify this. So just because it's not a perfect fourth doesn't mean that I can't maybe simplify it a little bit further. So 25 I notice is a perfect square. So I can write it as 5 squared. Okay, so deal with things that you know. You know 25 is a perfect square, so just rewrite it as such. Okay, 5 squared. Now, don't forget, I can rewrite this using exponents to help me simplify it and write it in an easier way. So I have 5 squared raised to the 1 over 4 because the index is a 4. Now, when I use my power rule, multiply the exponents together, right? Power raised to another power, multiply the exponents, you get 2 to the 4th, which we know is 5 to the 1/2. Now, if it wants you to leave it in exponent form, you can leave it like this. If it asks you to write it in radical form, we're just going to write that as the square root of 5. Remember, the denominator is your index, okay? And the numerator of your exponent is what lives underneath your radical. Now number 11, the sixth root of 216. So 216 is not a perfect 6, but I can use my exponents to help me rewrite this. Now if I take back a look at my list I wrote before, I'll notice that 216 is actually a perfect cube. So I can use that to help me when writing number 11 in simplified form. It may be easier for you to start out writing the sixth root of 216 as an exponent, which would be 216 to the 1/6. Now, if you just want to break up 216 into something that you know is perfect, which is 6 to the 3rd in this case, we now have 6 to the 3rd raised to the 1/6. Again, think of your power rule, multiply the exponents together. This equals 6 to the 3/6, which is just 6 to the 1/2, which is the square root of 6. Try number 12 on your own. I'll give you a few seconds to do that. So we're going to think about 9 as being a perfect square and rewriting it. So I can rewrite it as 3 squared. This is raised to the 1/6. So 3 to the 2/6 is actually 3 to the 1/3. And I rewrite that in radical form as the cubic root of 3. And if this helps, I'll just color coordinate it. So the 3 in the denominator of the exponent is the index of the radical. The numerator of the exponent is what lives underneath the radical, right? The exponent of the radicand. And my base of my exponent is the radicand. Please keep in mind that you can only multiply or add or subtract if the indices match, okay? So the index has to be the same in both radicals, which I mentioned a little bit earlier. And we know that because we've dealt with square roots, right? We can multiply a square root by a square root because they live underneath the same type of radical. Same thing with any other index. All right, and that's basically what we just explained. We can take the nth root of any number, multiply it by the nth root of some different number, and then all you do is multiply those numbers underneath the radical together, and the index remains the same. Looking at number 13, we have the cubic root of -8 times the cubic root of 27. Always first make sure that your indices match. That way you know you can multiply them together. They do. What I would also make sure to look for is, can I simplify these before I multiply them together and get this big number underneath the radical? Well, the cubic root of -8, we already said was a -2. And the cubic root of 27 is 3. -2 times 3 is 6. Nice and easy. Now the cubic root of 25 times the cubic root of -5. Now, since they both have the same index, I can multiply these numbers together. Cubic root of 25 times -5. That gives me the cubic root of -125. Now I can simplify that to just -5. Remember, I'm allowed to have that negative under the radical because it's an odd index. Number 15, again, all of my indices are the same. Now here we have subtraction and addition, okay? A little bit different than multiplication, and that's because we have to simplify each term first and then combine anything that's alike. So let's try breaking each of these terms up. Remember, break it up into its perfect and its not. So I can break up the 4th root of 64 into a perfect 4th of 16. Times the 4th root of the missing piece is 4, right? That's my not perfect. So the 4th root of 16 is 2. 4th root of 4 is not perfect, so it hangs out at the end. Let's move on to the next term. So from that, I'm going to subtract the 4th root of 32. Well, again, I can break that up into a perfect and a not. So the 4th root of 16 goes into 32. Times the 4th root of 2. That's my not perfect. So the 4th root of 16 is 2, and the 4th root of 2 hangs out at the end. Now remember, this is just like simplifying regular square roots that you've done since Algebra 1. Okay, so break it up into the largest perfect that goes into that number, and then its not perfect hangs off the end. And the last term is plus the fourth root of 81. Well, that's actually a perfect fourth. That's just 3. Now let's see what I can combine together. Nothing else, so that's actually my simplified answer. Remember, for these terms to be alike here, they both have to have the same index and the same number that lives underneath the radical. In this case, they don't. So that's as far as we can go. Number 16, I have multiplication, so I have to distribute. Let's multiply the first terms together. I get 2 times the cubic root of 16. Multiply my second terms together, and I get plus the cubic root of 64. Always try to look to see if you can simplify more. I'll rewrite my 2, and let's break up the cubic root of 16. Breaks up into the cubic root of 8 times the cubic root of 2. And that simplifies to 2 times the cubic root of 2, which is 4 times the cubic root of 2. And the cubic root of 64 is actually a perfect cube, right? So just plus 4 at the end. Can't combine them anymore. This is my simplified answer. Try number 17 on your own. Pause the video here. And remember, you're going to have to FOIL or double distribute here. And then don't forget to simplify at the end. After you double distribute, you should end up with a simplified answer of 9 times the cubic root of 2 minus 6. Take a look at that. If you need to, pause the video, see if you made a mistake anywhere before you go on. Now, the last thing we're going to cover today is simplifying radical expressions with variables. And remember, we've done this before, okay? The first example is something that you have seen before, right? We're taking the square root of 72 times x to the third. You're going to think about breaking it up into its perfect and its not. So, square root of 72, the largest perfect that comes out of that is 36. I can take out 2 x's, right? So x to the second. And now think about your not perfect or your leftovers. Well, my leftover is a 2 times just an x. So when I simplify my perfect, which will always be simplified, I get 6x times the square root of 2x. Remember, your not perfect remains underneath the radical. Let's apply that same thought process to the second example. Now I'm going to take the 7th root of something. So the 7th root of x to the 12th. Now your perfect part should be the same as your index. Or it could be a multiple of your index. So in this instance, dealing with the 7th root, so I can take out 7 x's. I can't quite get to 14, so I can only take out the 7, right? 14 is a multiple of 7. And now my leftover is the 7th root of x to the 5th, right? I have 5 x's left over. 7 plus 5 gives me my 12. So the 7th root of x to the 7th is just a nice x. And the 7th root of x to the 5th can't be simplified anymore, so that hangs off the end. Now, let's just look at this perfect guy here, okay, to see why it just became an x, if that blew your mind a little bit. So if we rewrite that, okay, if we think about this using exponents, just like we were doing earlier, I can rewrite this as x to the 7 over 7. Simplified, that's x to the first, right? So if your index matches up to the exponent of your radicand, it's going to basically cancel those out and leave you with your variable. I'm going to do the first practice example with you, and then you can pause the video, complete the rest and check your answers once you're done. So for number 18, breaking it up into the perfect and the not. So we're talking about square roots. So the largest perfect square that goes into 27 is a 9. Now I can take out at most 4 x's to make that perfect, right? 4 is a multiple of 2, which is my index. And I can take out y squared. Awesome. Now my leftover piece would be square root of 3, and I have 1 x left over. When I simplify, my perfect becomes 3x squared y, and then times the square root of 3x. Use those same steps, that same thought process, just be aware of your index in each of these. Pause the video now, try the rest on your own, and then you have a short homework sheet to complete once these are done.